Okay, so now let's discuss about question 8, which is compare decision trees, random forest, and boosting, highlighting strength and weakness of each. So let's see different decision tree. Yeah. So decision tree is basically a single unit or it recursively split features based on feature test. For example, we are building a decision tree where age it can either be less than 18 or can be greater than 18. For less than 18, we cannot vote. For greater than 18, we can vote. Right? Like that. Now let's see the strengths. That is, it is very interpretable. It is a white box model where we know what we are giving and what we are getting and how we are getting. Right? It handles the numeric and categorical features. It does not require much pre-processing like scaling and cleaning. Right? And it can capture non-linear relationship easily, unlike linear regression. Right? Then we have for weaknesses, we have they are highly prone to overfitting because it leads to high variance. Why high variance? Because the decision tree can train with more training data noise also. So it could lead to high variance and small changes. And another weakness is small changes in data can greatly change the tree structure, which is correct. Because if I change two or three records from a data set, then the tree will entirely change and computation would be done again, right? Then we have random forest, which is nothing but bagging plus random feature selection. Here we use a collection of trees, and each trees are given a bootstrap sample, which is sampling with replacement. For example, build many decision trees on bootstrap sample. Each split consider a random subset of feature. In each split, we consider a random subset of feature, right? And predictions are average. Whatever are the predictions made by those trees, those are averaged if it is a prediction of numerical value, or it is considered as mode if it is a categorical value, right? Then we have for strengths, it reduces the variance and overfitting caused by that of decision tree. Yeah, compared to a single tree, and it works well out of the box with default parameters. It can handle high dimensional data easily and are good for nonlinear interaction. Weakness is it is less interpretable than a single decision tree that it's often known as black box model. Here we know here we get the prediction, but we don't know what is happening inside, right? And it is more computationally expensive as number of trees increased, right? Now let's see boosting, which is adaptive boost, random XG boost, gradient boosting. This comes under boosting. Here, idea is to build a sequence of weak learners, usually a shallow trees, where each new model focuses on example of previous model. So basically, we are making a strong classifier with the combination of weak classifier, and one and every classifier learns from its previous mistakes done by the previous classifier. Right here, it can handle imbalanced classes very easily because misclassified samples are given higher weights so that that can be reduced. Here, let's see the strength. That is, it can achieve very high predictive accuracy, often top performance structure and tabular data computation. Yeah. Then we have weaknesses. It is sensitive to noise and outliers, especially adaptive boost. And we need more parameters for tuning, which can increase our training time. And in boosting, our training time is very large. So, which is another disadvantage for this algorithm, right? Now let's see the B part. B part says explain the architecture and components of Hadoop, that is HDFS, Yarn, and MapReduce, or describe Spark and its advantage over MapReduce, right? So let's see Hadoop architecture. Hadoop architecture is basically framework for distributed storage of big data, in which a single machine cannot store that big data. So we divide the big data into clusters of machine, right? Here, let's see the main component, which is Hadoop Distributed File System. It provides high throughput data access and distributed storage, where we have two component, master node and slave node, right? Master node is basically used to store the metadata, which is directory, block location, and slave node keeps the data of that particular node, and it provides high throughput and fault tolerance. For how fault tolerance? It replicates the data along multiple disks, right? Then we have yet another resource negotiator, which is a resource management or task coordinator for job scheduler, right? It has two components, which is resource manager and node manager. Resource manager is for master node, that is, it allocates resource among application of multiple clusters or multiple data, right? For example, CPU and memory. And node manager is for particular that node which is connected to the cluster, and it handles the task coordination and node replacement and node failures if any node is gets failed, right? Now let's see map reduce. Map reduce programming model is basically it provides a mechanism for parallel processing of those large data sets. It consists of two steps. First map and then reduce. Map is nothing but it gives processes input key value pairs and leads to intermediate key value pair. Now reduce converts this key value pair to associated with the same key. Now map task that runs in parallel, shuffle intermediate result, then reduce task compute the final output. Here, overall, if I talk about the summary, data is stored in HDFS, task coordination is done by yarn, and computation expressed as map reduce jobs. Now there is another framework which is Spark. Right, let me write Spark. It is a alternative of map reduce which uses a in-memory approach and uses a resilient data distributed data set. This resilient distributed dataset provides many features to us. That is, it provides streaming functionality, it provides machine learning applications on those dataset, and so on. Right? It also provides stream processing frameworks like Kafka's and all, and which is it is faster than the map reduce because in-memory approach is used. Right? So this is it for the Hadoop. Now let's meet in the next video.